Welcome back, quantitative students. Today we're going to continue with our conversation about economic functions, i.e. the cost, revenue, and profit, as well as market equilibrium using the demand and supply curves. But this time we're going to talk about them as they apply to functions that are not linear. We're going to start by exploring them as quadratic functions, and then we're going to finish up our lesson today with an overall review of parabolas and the graph of a parabola, of how the vertex works and what intercepts are. This is chapters 2.1 and 2.2. You can find this PowerPoint you're looking at here, as well as the video I'm creating right now on eCampus in week number 2 folder, submodule 2B. Let's begin by talking about some old nightmares that we remember from way back in the day. Literally 10 minutes ago, right? Here they are again. As you can see, the concepts still apply for quadratic functions because they still are economic models. So we are going to be still applying the concepts of revenue minus cost is equal to profit. We're going to think about, again, how the total cost is the fixed cost plus the variable cost. And as usual, the revenue is the price times the number of items X. Here are the old monsters I was talking about. For this particular chapter, we do require that you kind of dabble in your Algebra 1 topics. You probably recall studying factoring when you're in Algebra 1 and Algebra 2. These are the 7 different styles of factoring, 7 or 8 styles of factoring that appear. Good news, if you don't remember how to do them particularly, that's okay, because we're using Desmos a real lot here. The only difference, though, the only exception to that rule is when you do some of your homework in WebAssign, you'll see that they do require you to kind of walk through certain specific steps to get answers, and that's using the algebraic approach where you're using factoring and such. So in chapter 0.6 of your book, which by the way, we were just talking about how you should be able to access your ebook when you look at Cengage. And if you can, I'm here to help you. Please let me know and I will show you just where you could find it. But if you are having problems with factoring, which, you know, the F word, factoring, you can go to chapter 0.6 in your textbook. And in there, there's a lot of great examples and they show you demonstrations of it. And then you can do some practice. That's an old topic that we're kind of assuming that you're very strong on coming into quantitative analysis in the college level. Also, we're assuming that you're very familiar with this concept of the zero product. The zero product property states that, and this is the whole basis of solving quadratic equations, is that if you have 2 quantities being multiplied together and their product is 0, then it serves that it must be that one of those 2 quantities must have been 0, because you can never get an answer of 0 as a product if you multiply 2 things, unless one of those 2 things or both of them is 0. So we hold that closely to the concept of factoring and solving quadratics, because when you see an equation that is in quadratic form, remember quadratic means has x squared in it, okay? When you see an equation that has x squared in it like that, we first try to factor it, setting it equal to 0, because then we can state that the 2 things in the parentheses could equal 0 when those would be answers, and that is the 0 property. They lean on that a lot in quantitative analysis because 0 is the time when your profit equals 0 is the time when you have a break even. So making it equal 0 kind of like keeps on coming back to haunt us. So just remember, polynomial nonlinear equations, they can be solved with factoring if you factor them first and then you apply the 0 property. That's the old school algebraic approach of how to solve equations that are nonlinear. Now, we're going to do them with some ideas, but most of them we're going to conquer using Desmos. So let's jump in with solving some quadratic equations, and I'll show you now how to get answers using Desmos. Recall that we promised you could solve any equation in Desmos if you just use the left side of the equation and the right side of the equation and see where the 2 lines cross. In the first example I have here, you'll see it's 6x squared plus 3x and 4x plus 2. Here's how I'm going to solve this in Desmos. First, I'm going to go ahead and say y equals this right here, and then I'm going to do another y equals, and I'm going to do y equals this right here. So let's go into Desmos now and see what that looks like. Recall when you're in Desmos, close everything out. Get the home button to get back to your home. And let's put y equals, and now I'm going to just type exactly the left side of that equation that I just saw. 6x squared plus 3x. Surprise, it's a parabola. Right? All right, let's take y equals, and now let's look at the other one. The other equation that we did was 4x plus 2. That's the right side. Now, where do they cross? Well, guess what? They cross in 2 different places. Take a look at where they cross. They cross here at negative 0.5, comma 0. And they also cross here at 0.667. Now, you might know off the top of your head, 0.667, that's kind of like 2/3, right? You probably know off the top of your head, negative 0.5 is negative a half. That's why the solutions to these two equations are as you see right here. This number and this number are the two solutions to this equation. If you were doing something where you were talking about the number of items that you were producing, you would discard negative 0.5 and say, I can't make negative items. The answer is 2/3, or it might be 2/3 of 1,000 or 2/3 of 1,000,000 or whatever, okay? So that's how you would go about solving an equation. Remember, if you're solving something quadratic, you can either do it with the old algebra using factoring and solving the equation with it equal to 0, or again, you could use Desmos by saying y equals the left, y equals the right, and see where they cross. Remember, the answers to your solution, the answers to your equation are going to be only the x values, the things that I highlighted with red boxes. The y values are not the answers, it's the x values. And with a quadratic equation, you can almost always expect exactly two equations. Sometimes once in a blue moon, there's repeat answers, but you could always have two solutions. And here the two solutions are negative a half and positive 2/3. Okay, let's go back and look at that other one. The other one is 6x squared equals 9x. So like I said, I'm going to say y equals the left and y equals the right. And then I'm going to see where they cross. So it's 6x squared and 9x. Let's go back. Again, close everything out. Go back home. Y equals 6x squared. And y equals 9x. And this is one of those examples where there's one and only one solution. Look closely. Where do they cross? This time it happens to cross exactly in one and only one place, at the place where x equals 0. That is the place, that is the only solution to this equation that will fit. Okay. All right. Some more cases of equations here. They came out a little bit backwards. Okay, and example 2, solve by factoring. Here, once again, I have two equations. And friends, I'm going to encourage you when you do these equations to go ahead and do y equals the left side and y equals the right side. Notice that for part A, the variable that they like to use is y. So that's not a really big deal. Just change it and make them all x's. I'm going to do that right now like this, so quick and easy. Okay, x minus 3x plus 2. So go in and do them. It would look something like this if you did them. X minus 3 and x plus 2. Just the way you see it. Don't think too hard about it. There it is. And then put the other one in. It's negative 4 on the right. Y equals negative 4. Where do they cross? Down here, they cross at negative 1 and 2. The answer is negative 1 comma 2. And then for the last one, you can see it's kind of complicated and ugly looking. There is something important to mention here. Notice that we have conditions on the variable. What I mean by conditions, if you remember, is the denominator here. What if I think x equals 0? You're going to have a problem because when you go back to substitute and check x equals 0, you're going to have no value for this first fraction here, 3 over x. Likewise, you can't let x equal negative 2 because can you see that negative 2 would give you that as an answer as a 0? And so you'd have a problem. What that means is when you go through the actual solving of these equations, if you find an answer in your algebra that looks like 0 or like 2, or negative 2 rather, you should know to discard them. Otherwise, you would write in there y equals all of this stuff, and y equals all of this stuff, and see where they cross. I'm not going to do that with you right now. I'm not going to waste your time. We just did 4 examples of it. But this is how you solve equations in Desmos, friends. You do y equals the left, y equals the right, and see where they cross. It's that simple. So let's not try to do the hard algebra. Let's use technology and apply that, because I need you to be able to think more about the actual economics and the concepts of the costs and such and all those different things. The algebra is a secondary skill set here, okay? Now, let's talk about quadratics a little bit. Here are some applications of quadratics. This is your age-old typical example where you're supposed to read the question and come up with an equation and then solve the equation. With this one, I want to make you remember the idea that you don't necessarily need to know every little detail of every science that's out there to answer these questions. This is an example that actually comes from physics. In this case, if you follow the idea and you look very closely at the way it's worded, you'll know what to do. If you're not familiar with physics, you don't really need to be. So let's remember where it says this is the equation, you can just kind of blindly believe it. I think that the thing that confuses students when they do applications in mathematics is they may not necessarily particularly know why d of t is that strange expression. We don't need to know that. That's up to physicists why that's the question. What we need to know is how to answer the question using math. So let's read the question. I'll show you what I mean. A tennis ball is thrown into a swimming pool from the top of a hotel. The height of the ball from the pool is modeled by this function in feet, where t is the time in seconds after the ball was thrown. So how long after the ball was thrown then? Was it 144 feet above the pool? Now to answer this question, what we have to do is recognize that 144 feet is 144 feet is actually the value of d of t here. And the equation that you actually want to write is what you're looking at here, including d of t being replaced with 144. Would look something like this. Let's write it out. And don't forget there's a squared there. Let me insert my squared right there. Okay, there's my squared. So what I did was I just replaced d of t with 1400, and now you're back in Desmos where you're writing y equals 1400 and y equals that other expression. We see what we get when we solve it. And when you solve it, this is what happens. You get the answer of 3. You get exactly 3 as your solution. Let's go through it anyway, just as one more example of how to use Desmos. I'll say y equals the left side right here. And then I'll type in y equals the right side, which is all this right here. Let's take a look at it in Desmos. Close all my old windows. Click home. We don't have to click home because we are home. Remember that the left side is y equals 144. The right side is y equals negative 16t squared. Now I'm going to use x instead of t. Minus 4x plus 300. All right, now, looks like 2 black lines. Let's zoom out and see if they cross with something else somewhere. And I could see now where they cross. There they are. If I click on it, I have 3. If I get a little bit closer, I can see how it crosses here. You see, of course, that's the intercept, but it crosses here at negative 3.25. It also crosses at 3. The answer is at x equals 3 or time equals 3 seconds. Remember, this is time. So like money, you can't have negative time. So we would not say negative 3.25 or 3. We would discard the negative 3.25 and we'd say the answer is 3 seconds in is when it would be 144 feet above the pool. Now let's talk about the square root property. The square root property states that if you want, you can square root both sides of an equation, but please be advised, as soon as you do that, you show up with 2 new equations, not 1 new equation, but 2. If, for example, you say x squared equals 9, right? X squared equals 9. When you square root both sides, you have x equals plus 3 and x equals minus 3. You have 2 answers, and it is true that there are 2 numbers that will fix that sentence. If x squared equals 9, you could put 3 in there to make it right. And you could also put negative 3 in there to put it right. So the point is, when you square root both sides, and I'm talking about this particular place right here, and over there, when you have an equation like x squared equals c, say for example, c is 9 or something like that, whatever it is, if you want to square root both sides, please do so. You could do that. But when you do it, make sure that you include plus or minus c. The answer is x equals plus or minus 3, not just 3, but plus or minus 3. That is a square root property. Now, again, in the case of t equals time, x equals the number of items, dollar amounts, of course, you can't have negative numbers, and that's something we all already know. But generally, for algebraic purposes, when you're square rooting both sides of an equation, it is practical to include plus or minus before you start making judgment calls about the application being economics or whatever to discard a negative answer. Let's take a look at some examples that use the square root property. Here we have two cases. For this, the way I would go about it is I'd start by dividing both sides by 4, like this. Let's come up here and finish that. And then what happens is I have x squared equals 5/4. Okay, I'm changing color because now is that important time we're going to square root both sides. Here I go. And when I square root both sides, the thing on the left does become x, but remember the thing on the right does become plus or minus. And the square root of 5 on top is the square root of 5. The square root of 4, by the way, on the bottom is just 2. This is the answer we're looking for part A. I hope that makes sense. While we're in this conversation, take a look at part B. In part B, I would, and I'm going to use black for this one. In part B, let me clear that out. Since I have something squared on the left, I might as well go right in immediately with the square root. And when I do, I wind up with two equations. The first equation is 3x minus 4 equals 9. I'm sorry, not 9. 3. And then the other one is 3x minus 4 equals -3. Solve these two using old school algebra and you get two different answers. Or, like I said earlier, you could say y equals the left side and y equals the right side, and you'll see the two things intersecting in two places. Those two places are the two solutions you're about to get here as well. So you could do it with old school algebra or you could do it with Desmos. For the WebAssign practice, you'll have to demonstrate the specific steps of doing, for example, here we have the square root property. Otherwise, I would always lean on Desmos to get solutions for something like that. Let's go through what it would look like doing this one in Desmos. The left side being this, the right side being this. So I'll write in y equals the left and y equals the right. Let's go to Desmos and take a look at that. It's 3x minus 4 quantity squared. (3x minus 4 quantity squared). And then the other thing is y equals 9. So we do that, zoom out, where do they cross? Here they are, what are the answers? The first one is, let me get a little bit closer, I can't tell if it's the intercept or what. The first one is 0.333, you know that's 1/3. The last one is 2.333. So you can, if you click the dots, they become black and then you can see what the actual numbers are. Don't forget, friends, when you're solving equations using Desmos, that we have to use only the x values as our solutions. Don't look at the y values. All right, so that's what the that's what the square root property is. Again, you can bypass it completely if you use Desmos anyway. Here are your solutions, by the way. I just worked out for you the two numbers. Now, the last resort, the quadratic formula. So if you're using factoring the F word and that doesn't work, if you're using graphing and that doesn't work, and if you're using the square root method and that's not working, it might be because when you do this equation, it has a funny irrational root that might be the square root of 7 or the square root of 21 or some odd square root. And if that be the case, then the only way to get your answer is to get it through the quadratic formula. Please be advised, friends, when you're doing WebAssign homework, if it says please include exact answers only, then approximations from Desmos in decimals will not suffice and it won't grade it correctly. So if you're in a situation like that, it may require that you move through the quadratic formula to get your solutions. Here's a great case of how you will go through getting the answer to a quadratic using a quadratic formula. Recall that it follows the concept of if you can think about the coefficient of this being A, then the coefficient of this next one is B, and then this is C, then you can put them all into this formula. So in this situation, here we would say A equals 2, B equals -3, and C equals -6, and work through the question to get our solution. And then we would use our formula and get our solution. Now, I'm not going to go through that because I know that you've done that in the 7th, 8th, 9th, 10th, 11th, and 12th grade. But in other words, be prepared, friends, to use the quadratic formula to solve some of these as well. Right. The answer, by the way, to that one, as you could see, is 3 plus or minus all of that you see there. If you had a question like that in Desmos, they would require you to write it using that square root right there if it said that you could not use approximations or that your answer had to be exact. So look closely at your Desmos and your exams, and remember your answers have to be exact when you do some of these, and if they're not, you have to use the quadratic formula. All right, so for example 6, we have the case of a non-real solution. Using the quadratic formula, find the real solutions to this. The easiest way to do that is use Desmos. If you use Desmos, you'll see that those two graphs do not cross, x minus 1 and y equals x squared. They just don't cross. There's nowhere where they intersect. If you did it using the quadratic formula, then when you got to this part, when you got right here, I guess you can't really see that. The thing under the root will wind up being something negative. And just like you're not allowed to divide by 0 in algebra, you can square root things, but that brings you to a new imaginary level of complex numbers. Generally, solving real equations, especially economics like cost and profit, if you're square rooting a number and it's not and it's negative, you're not going to get an answer. So in other words, sometimes when you solve a quadratic equation, you just don't get an answer because the quadratic formula will tell you the thing under the root is negative and you can't finish getting a value. So in the case of example number 6, when you go through the work there, solving it for 0 first, a equals 1, b equals -1, and c equals 1, if you plug them all in there together, you'll notice the thing under the root is negative. That thing under the root, by the way, that's called a discriminant. You might recall that from your Algebra 1 lessons. If that number is negative, then there are no real solutions. All right, I hope you guys are having fun. I sure am. Let's talk about applications with quadratics now. Here we have an example of the Social Security Fund. The Social Security Fund trust balance, B, in billions of dollars can be shown using this function. T is the number of years past 1995. So for planning purposes, it's important to know when the trust fund balance will be 0. To find this, solve the equation you see below. Now, in this particular case, remember how we discussed that oftentimes we have to align the data. Here we have a case of aligning the data based on the value of T being years past the year 1995. Now let's do a basic example. What if T equals 3? I guess we mean year 1998. What if T means 10? Well, then I guess it's the year 2005, and so on and so forth. So when I solve this equation here using Desmos, which is really very easy to do, I'm going to get an answer, and whatever that answer is, I'm going to add it to the year 1995. Let's go into Desmos and get a solution now. Okay, of course we have y equals 0. Now y equals 0, for those of you who know, y equals 0 is just the x-axis. As you can see, the x-axis has been highlighted in green to represent the line x equals 0. The right side of that equation was a little ugly. Y equals negative 7.97. X 97. What happened to my 97? X squared plus 312 to x plus, I'm sorry, not plus, minus 356. Now, it may look like a straight line, but it certainly is a problem. It's just a really, really humongous problem. Let's zoom out and take a look at it. There it is. And where does it cross through? Well, it crosses through in 2 places now, does it not? It crosses through at 1.176, and it crosses through again at 37.97. What does that mean? That means 1.196 1995 plus 1 is 1996. Here it's 37 or approximately 38. What's 1995 plus 38? 2023? Wait, plus 38. 2033, right? Okay, so that's what we were looking for a question like that. Let's reveal the answers now. You see there are solutions. And it will be in the year 2033. There is also a second solution, like we mentioned, that's not listed here, associated with the very first year, but that's only based on years past 1995. That may be why that doesn't work that way. Okay, now, We're about to start chapter 2.3, which is the last thing we're going to study today, chapter 2.3, and it's the geometry of parabolas. Here, let's start by talking about what is a parabola. Whenever you graph any function that has x squared in it, it's going to be a bend or a curve like you see here. We like to call it a bowl and an umbrella. You might have heard it being referred to as a happy smile and frown, happy face and sad face. All those things kind of apply. Concavity is part of the story as well. In the case of a parabola, we always have a vertex. The vertex is a special place in the parabola where, as you travel through the parabola, it stops decreasing and then starts increasing right at that special place, like you see right there. That vertex is always going to represent either a maximum or a minimum value for the parabola. In the top picture there, you'll see, since it is something of a smiley face, the lowest point is the vertex, so the vertex represents a minimum. Let's connect that concave up or smiley face or positive look represents a minimum. Then, in other words, if you have a bowl catching rain, the bowl will touch the middle bottom of it first, and that is a minimum. Now, in the case of a vertex here on the bottom example, we have the vertex being at the top because we have a parabola that is concave down or looks like a frown. So try to remember when it looks negative or like a frown or like an umbrella that you have a maximum. And if water was dropped down on top of it, it would touch the top of it first, not the bottom of it like a bowl, but the top of it first, making it a maximum value. So once more, a sad face frown has a maximum value. So that opposite idea exists in parabolas, and it's important you know, if you're thinking of a parabola with a max, that means that it must be an umbrella looking one. If you're looking at a parabola that has a minimum, it must look like a bowl or a smiley face. Okay, so let's remember that. Again, I know that's old news. You learned that in Algebra 2, right? Here are some other important ideas about parabolas you need to know. We remember this vocabulary. A quadratic function is a function that has x squared in it. The parabola is the beautiful shapes that you see on the right that represent the graphs of quadratic functions. The vertex is that important turning point where the graph stops falling and starts increasing, or vice versa, and it represents a max or min in parabolas. And last but not least, we have something we like to call the axis of symmetry. The axis of symmetry is not really used very much, but it's another geometric concept. Here, I'll draw them for you here. They go right through the axis, like this. There's your axis of symmetry. So wherever the vertex is the axis of symmetry, of course, will go straight through it like so. So how do you find the vertex of a parabola? Well, it's a very long, complicated, ugly story, and you learned about it in Algebra 2. You could do it by changing the format of the quadratic from standard into vertex form. You might remember doing that. That involves factoring. You could also do it by completing the square. You might remember that horrible lesson in algebra, right? Here, I am here to tell you once again, you don't need to use any of those ideas because you have Desmos. So when you're looking to find the vertex of a parabola, it's very easy. You just put the equation right into Desmos, click where you think the vertex probably is, and it will pop immediately, and it will tell you right then and there what it is. It's very simple. So you don't have to think very hard about it. Here's an old school formula for finding the parabola's vertex. If you can format it such that, let me get a little bit closer so you can read it with me. If you format it such that it's in standard form, in other words, like it's ready to be used for the quadratic formula with a, b, and c, then you could use those values a, b, and c to get the x value, and then plug that x value you just found into the function again to get the y value. That's what this writing means. So there is a way to figure out the vertex algebraically. Once again, my friends, I strongly recommend you just go straight to Desmos and don't even mess around with any of this stuff. Know it, however, because when you do your WebAssign, you will have to demonstrate the little nuances of finding that vertex in different ways. Okay, so we have that formula with negative b over 2a, we have completing the square, and we also have changing from standard form to vertex form, but you don't need to know any of that because the good news is you have Desmos. So here's a great example. Example 1, please find the vertex and please sketch the graph of this function. And you could see it's a simple parabola, 2x squared minus 4x plus 4. Let's go on over into Desmos. And let's clear everything out of Desmos again. And now I'll type in that formula, y equals 2x squared minus 4x plus 4. The next one, and let's just, okay, that's it. There it is. Where do you think the vertex is? Probably here. I'm going to click kind of around here and look, the gray dot appears. Let me click the gray dot. 1, 2, there's the vertex. So when it comes to finding the vertex, what a piece of cake. Don't you wish we showed you Desmos when you were back in Algebra 2? You didn't have to do all that hard work you did to make it through Algebra 2. So that's how you're going to find a vertex, my friends. You're going to graph it right here in Desmos and just click where you think it is and just take the answer right out of Desmos, and you'll be able to always get them right. All right, here we have a basic algebraic concept, 2x squared. You'll see, of course, very large dollar amounts, 200,000 x squared and 0.51x in very strange values because we're trying to make them real world practical applications. So just get ready for that. All right. When you graph it, it looks kind of like this. If they want you to provide a graph, remember that you can go in and change the axes accordingly based on whatever you think you might see there in WebAssign for your multiple choices. Let's do an application now. Here is a profit function. Can you find the number of units that give the maximum profit and that give the minimum profit? The number of units that give maximum profit and that find the maximum profit. So this right here, and I want you guys to pay close attention with me to this, okay? This concept, the number of units that give the maximum profit. Yeah. That's going to be X. And then this concept here that we have going on, the maximum profit, that's going to be Y, right? Yeah. So in code, they're saying, please find the vertex, right? And it's important that you know, remember what X is. X is always the number of units. And what is this? This is the profit function. So what will Y represent in that point of the maximum? Y will represent the maximum profit. So what we're going to do is go ahead and graph this. And then we're going to see where the vertex is, and we're going to use that for our solutions. Let's go back to Desmos now. It's negative 0.1x squared plus 300x. Don't forget, friends, to make it y equals first, of course. Plus 300x minus 1200. All right, looks like a line, but you know it's a parabola because it has x squared in it. Let's zoom out and see if we can get a sense of this parabola. All right, let's see, where is it? Oh, it's all the way up there, huh? Yeah, it is all the way up there. Looks like it's right about there. I could even, let's zoom in a little bit better. Yeah, I could even click it now. Let's see, can I get the answer? There it is. So what is the maximum amount of units you'd make to make the best profit? The amount of units that you would want to make that would make the best profit is 1,500 units. What would the profit be? It would be $226,200. By the way, note there are other points on this graph. For example, you could have made 2,020 units, but look at what your profit would have been. It would have been less. You also could have, if you wanted to, made 722 units, but again, look like your profit would be less. This is a great example of trying to figure out how many units you should make to capture your highest profit. All right. So there's your solution of what you were looking for that question. Now we're talking about intercepts. When you're graphing a quadratic, it is kind of important to know that the intercepts are the places where it crosses the x and y axis. Intercepts, whether they're quadratic or linear or any kind of function, always have the same property that way, that one of the values is 0. If the x is 0, that means it's a y-intercept. If the y is 0, that means it's the x-intercept. We can find them easily by going right to Desmos. Something else that's important that we need to remember, and I'm going to really stress this for you because this is an easy thing. This concept here, that just means if A is positive. Here, this just means if A is negative. When you're looking at an equation of a parabola, if the x squared coefficient is positive, you can assume it's a smiley face happy, right? But if it's a negative coefficient, like in the last one, negative 0.1x squared, you'll notice it was a frown face and it was a concave down. So can we remember that the A value or the coefficient of x squared, that sign will dictate whether it's up or down, and you can always just use it as a quick guide to which one is which. So if you have many equations and you want to know which one is which, it's very easy to see if you just look at the coefficient of x squared. Negative coefficients go down and positive ones go up. So here's another example of a graph for a quadratic function. For this function, determine whether its vertex is a minimum or maximum, and then find the zeros. The easiest way to do that is to just look right here at the coefficient of x squared. You'll notice it's -1. That immediately means that it is a concave down parabola, something like this. And if it's something like this, doesn't that mean that there is a vertex on the top that is a maximum? So I already know just by looking at the equation, it's got a max in it. Also, if I want to find any zeros, the best way to go about that is to really just go right into Desmos and see where they cross. Let's go ahead and graph it. Y equals 4x minus x squared. Did I copy that right? Let me just check it. Yeah, 4x minus x squared. Okay, so where are the intercepts? Well, here's the vertex, 2, 4. Nobody asked about it, but that's the vertex. And by the way, like I imagined, it is a max because this is the frown face. What are the intercepts? 0, 0, and right here, obviously, 4, 0. So again, Desmos really makes it very clear and simple how to find not only the vertex, but also, of course, the intercepts of the parabola as well. So please lean on it heavily to answer your questions when you're doing your web assignment practice, because I'm not interested in your ability with parabolas. I'm more so interested in your ability with understanding the economic functions, the profit, cost, and revenue, and the other ideas associated with market equilibrium, supply and demand. Here's your answers. That's what it would look like we just showed in Desmos. Again, if you had a question in WebAssign, you could compare it by changing the axes if you needed to. Here's a great example of graph comparison. For part A, determine the vertex of each function. I would definitely look very closely here and try to figure it out by looking at it, but that's the kind of thing that you might not necessarily be able to get looking at it. The vertex of the function is definitely going to be right about here. I'll use a star to show it, and right about there, of course. You can't see the star, it's yellow. Let's make it hearts. There you go. So there you go. Lovely vertices, right? Okay, so there are your vertices. Determine the vertex. What kind of, think about where it kind of looks like it is. I would do something kind of like this, and try to do it that way to figure out what it might be. Ultimately, later on, we have the examples of what they might be, and you can determine which one is which, and based on that, you can get them for sure. So part A is not really the best question to start with. We should start with part B. We'll come back and visit A in a minute. For B, it says, determine the real solutions of f of x equals 0 and f of x equals 0. See how it says f1 of x? That just means the first function. So when is it the case that y equals 0? Specifically at these places. Y equals 0, right? Here, at -1, and right here at 7. For this one, y never ever equals 0. So in the case of part B, there is no position for where it equals 0. And last but not least, it says for part C, one of these graphs is this and one of them is that one. Which one is which? The way we're going to get the answers for that, let me zoom in there. You'll notice that one of them has a negative coefficient and one of them has a positive coefficient. Of course, it's this one here that represents this one here. And likewise, the one with the positive coefficient is the one on the right. Knowing which graph is which, I should be able to now go and put those graphs right into Desmos, y equals 7 plus 6x minus x squared, and get what the actual vertex is that way. That's how I would answer part A. I would skip A and come back to it after I knew what the actual formulas were, because you can't really particularly see really well looking at this graph. You might be able to estimate it, but Desmos won't exactly let you go unless you have it exact. And that sometimes does require that you know the actual formula. So if you're in a position like this, please come back to this question. And remember what I'm telling you, that if you're looking at a graph, you might not be able to see what the actual vertex is unless you have the actual function. So here are the solutions that we wanted for that one. And part C, we explained the answer. That the first one is the first one, the second one's the second one, using the coefficient. I appreciate your attention, my friends. We are almost done. I only have 3 more slides to throw at you, and then we'll be done. This is our last topic. And once again, thank you so much for your close attention. This is the last thing we're going to do today. It's called average rate of change. What is the average rate of change? Well, it's a real lot of heavy, complicated, unnecessary wording to tell you basically the slope. It's the slope. That's all the average rate of change is. When it comes to a function like the curve that you see down there, the slope, if you give it 2 points, is going to not be constant every single time. For example, if I had 2 points on that function, and I'm going to use hearts again. If I had 2 points on this function, say this point and this point, I can find the slope of those 2 points by using the old school slope formula, m equals y2 minus y1, etc. You could see that right over here. This is the slope function ultimately, after all, right? That's the slope formula. What they do is, instead of saying, well, for this curvy function, there's a slope, there is no such thing. Instead, we don't have a slope, we have the next best thing, which is an average rate of change between 2 specific points given already on the graph. So if you want to find the average rate of change, what will happen is they'll give you 2 values. They'll tell you x1 and x2. What you do is you use the formula to go and calculate what y1 and y2 are, and then use all 4 of those variables in the slope formula, and that's the average rate of change. It's really very simple. They make it unnecessarily complicated in the high school math books. It's just the slope again. Instead, this time you don't have a straight line, you have a curve. So whenever you find the slope, it's not constant. It's not going to be like a linear function such that you could pick any 2 points, and it will always be the same slope. It will be different based on what 2 points you're given out of the function for the average rate of change. Let's do an example so you can see what I'm talking about. In this example, we're saying, can you please figure out the average rate of change for this function from one value of x to the next? Take a look at this case. We found that the revenue for the cruise, for example, 5, was given by this function, and we have a function there. X is the increase in the group size beyond 50 people. Now, what is the average rate of change of revenue per person if the group increases from 50 to 55 persons? The first thing I need to point out to you, my friends, is if we're increasing from 50 to 55 persons, and X is the group size beyond 50, then this should be rewritten to be from X going from 0 to 5. Like so. And now what I have to do is use those 2 values, 0 and 5, and put them into this function to find out what R of 0 is and what R of 5 is. Okay, so if we're going to do that, what happens when I put 5 in there and what happens when I put 0 in there? Easiest way to do that, guess what it is? Let's go to Desmos. So first what I'll do is I'll put that function in there. And you could do this in a lot of different ways. This is the most direct and easy way to do it, I recommend. Let's put the function in just the way it is. Y equals 1500 plus 5x minus 0.50x squared. Now I'm going to go and take that function and turn it into a table with the gear and click the table. Can you please tell me the value at 0? Here it is, 1500. Can you please tell me the value of 5? There it is, 1512.5. This information right here is what you need to figure out the average rate of change. These are the 2 points. And we're going to act like those 2 points are going to be on a straight line where we're finding the slope. 0, 1500, and 5, 1512.5. Something like this. M is going to be y2 minus y1. And x2 minus x1 is going to be 5 minus 0. Something like this for your slope. All right. Now on the top, that becomes 12.5. On the bottom, it's 5. And then we divide those. And I'm getting 2.5. Case in point, the average rate of change this time is 2.5 or $2.50 per ticket. So let me just reiterate once more what we did. We were given a function and we were asked to find the average rate of change from 0 to 5. Of course, the application was from 50 to 55 with alignment and so on. But the bottom line in algebra was, here's a function. What is the average rate of change from 0 to 5? So what we did was we found out the y value when x is 0, as you can see in the first box. Then I found the y value when x was 5. That's in the second box. I used those two pairs as points and applied the slope formula because, like I said, the average rate of change is simply the slope, but applying it to two specific points on a curve instead of any 2 points on a straight line. So here we do the arithmetic and we get a final answer of 2.5, telling you that the answer for the average rate of change for this particular story is $2.50 per person. The last thing I want to talk to you about, and guys, this is really very crucial. We are about to dismiss, so I want to tell you once more about our forthcoming plan. Tomorrow, we were going to meet to talk about chapters 2.1 and 2.5. 2.1 and 2.2. We're not going to need to do that anymore because we just did that. So now tomorrow we are not meeting for class. However, everything is open for you and ready for you to go and start doing your homework and getting ready to do that section. Also, next time we meet will be this Friday, but it's optional. You don't have to come. I will be here on Friday at 4:30 if you have any questions about your homework or about the exam or about the exam review. On Monday is your exam. Here are the details about the exam you need to be aware of. Exam number 1 will be available at 4:30 on Monday. It will be there until 9 o'clock, but you will only have 2 hours to do it from the moment you opened it. In other words, you should start at 4:30, but if you need to, you can start at 5 or even 6 or even 7. But if you start past 7, you're going to get it cut at 9, and you should have 2 hours to do it. So try to make sure you start before 7. Next, questions will be varied in form from student to student and in order and in values. So everyone will be getting a different variation of the test. Your grades and the answer guides will be revealed in a few days because I can't show you the answers until everybody has completed the exam. So everyone, please make sure that you get it done. And if you don't get it done, you will be receiving a 0. You have one and only one day to do it. Please don't miss your opportunity. It is recommended that you do the exam review beforehand. The exam review does not carry credit. It does not have to be done. It's not mandatory, and it's not one of your homework assignments. However much percent of it you complete will be available to be seen on WebAssign, but it will not be part of your grade. I recommend you carefully go in and try to do it and try to understand all the topics in there before you dare to take exam number 1, because exam number 1 is very closely linked to exam number 1 review. And last but not least, remember, no video lecture tomorrow and only optional attendance on Friday. If you want, I will be here to explain questions if you need me. If there's nobody here, I will not be here. I'll be here at 4:30. If you don't come at 4:30 and there's no one here at 4:35, I'm closing the window and I'm gonna not be here. But if you're here and you have a question, 4:30 is when I need to see you, okay? And my friends, I do genuinely appreciate your very close attention to my lesson, and that's all I got for you. I told you we would get out of here early. I promised you, and I'm keeping the promise. I'm even doing better. I'm letting you go even 10 minutes earlier than I said I would. It's only 5 after 6. Let's take attendance quickly. Got it? And I appreciate your attention, guys. We're going to break here. If anyone has any questions, you can stick around afterwards. I'm stopping the recording, and I hope everybody has a great day.